Welcome to UGC lecture series BSc Physics Honors Semester 6 Statistical Physics Lecture 12. In this lecture, we are going to discuss about Fermi Dirac statistics. Under the Fermi Dirac statistics, we are going to derive an expression for Fermi Dirac distribution law. In this Fermi Dirac distribution law, number of particles in a given energy level can be obtained. A mathematical expression for number of particles in a given energy level can be derived under this Fermi Dirac distribution law. Velocity distribution of particles can also be obtained, but we are going to concentrate in the number of particles in the energy level. Next, thermodynamic functions of an ideal Fermi gas. You know ideal gas, a gas which obeys ideal gas equation. Here fermions can be treated as an ideal gas. So, that is ideal Fermi gas. Thermodynamic functions like entropy, energy in the sense total internal energy, then specific heat capacity. These are all thermodynamic functions. We are going to see the expressions, mathematical expressions for this thermodynamical functions of ideal Fermi gas. Then summary about these concepts. These are all the things we are going to discuss in this lecture. Fermi Dirac distribution law. You know, Fermi Dirac statistics is obeyed by indistinguishable half integral spin particles. Half integral spin in the sense total spin of the system will be a multiple of 1 by 2. That is the meaning of half integral spin. Example for this half integral spin, the value examples for this half integral spin is 3 by 2, 5 by 2, 7 by 2, etc. So, particles which obeys Fermi Dirac statistics will be having half integral spins, and these particles are indistinguishable. Then with regard to wave function of these particles, wave function in the sense we have to go to quantum mechanics. Quantum mechanics gives a function, wave function for every physical system. Here the particles are assumed as physical system. So, wave functions of these particles have antisymmetric wave nature. So, these particles have antisymmetric wave function, and these particles obey Pauli's exclusion principle. Pauli's exclusion principle says that no two particles can lie in the same state. That means no two electron can have all the 4 quantum numbers same. This is the exact statement of Pauli's exclusion principle. Particles which obey Fermi Dirac statistics will obey Pauli's exclusion principle. So, these are all the conditions for a particle to obey Fermi Dirac statistics or to follow Fermi Dirac statistics. Now, derive a distribution law for a physical system. For that, consider a physical system. The physical system consists of n indistinguishable particles. Then these n indistinguishable particles are divided into quantum groups. Quantum groups in the sense principal quantum number can be the identity for the quantum groups. So, these n indistinguishable particles are divided into quantum groups such that n1, n2, etc., ni. These are all the labels of the quantum groups divided of the n indistinguishable particles. Then energies of these quantum groups are denoted as epsilon 1, epsilon 2, etc., epsilon I. So, the assumed n indistinguishable particles are divided into quantum groups like n1, n2, n3 having energies epsilon 1, epsilon 2, etc., epsilon I. Let Gi denote the degeneracy or statistical weight of the ith level. You have divided the indistinguishable particles into quantum groups. These quantum groups have energy levels. These energy levels may be degenerate or non-degenerate. Here, in the derivation of Fermi Dirac distribution law, Gi denote the degeneracy of the ith energy level or ith state of the particles. Now, we have to find the probability for the distribution of Ni Fermi particles in Gi eigenstates. Here eigenstates refers the energy level of the physical system assumed. In that physical system, n number of particles are there. Here we have to find the probability for the distribution of Ni Fermi particles in Gi eigenstates. To get the probability of distribution of Ni Fermi particles in Gi energy levels, we have to make some assumptions or conditions. Three conditions are made in Fermi Dirac statistics. Following are the three conditions. First one is, there is no distinction between the different ways in which Ni particles are chosen. You are assigned n number of particles. Those n number of particles are divided into quantum groups labeled as n1, n2, etc. Ni. Then we have to choose groups among these divided quantum groups. In choosing the quantum groups, there is no distinction. In choosing the particles, there is no distinction. So, that is the first condition. There is no distinction between the different ways in which Ni particles are chosen. Then the second assumption or condition is, the particles obey Pauli's exclusion principle, according to which each sublevel or each cell may contain 0 or 1 particle. Therefore, the energy level Gi must be greater than or equal to the number of particles Ni. So, this is the second condition. Now, the sum of energies of all the particles in the different quantum groups constitute the total energy of the system. You have assumed a thermal system. In that thermal system, n number of indistinguishable particles are there. Those n number of indistinguishable particles are divided into quantum groups labeled as n1, n2, etc. Epsilon 1, epsilon 2, epsilon 3, etc. are the energy levels of each quantum group. To get the total energy of the system, just sum all the energy levels, that is epsilon 1, epsilon 2, you will get a mathematical expression epsilon 1 plus epsilon 2 plus epsilon 3, etc. In a simplified form, it can be given as a summation over I is equal I to n epsilon I, summation between I to n of epsilon I will be the total energy of the system expressed mathematically. This energy is obtained by summing all the individual energies. These are all the conditions to derive Fermi Dirac statistics. Now, let us come to the derivation of Fermi Dirac distribution law. Again, remember that Fermi Dirac distribution law gives the number of particles Ni in the energy level Gi. We know that due to Pauli's exclusion principle, all can get more than one particle. So, all energy levels can get more than one particle. So, among Gi cells, because we have divided the total energy into Gi cells, only Ni cells are occupied by one particle each. Only Ni cells are occupied by one particle each. So, there will be some cells remaining. The remaining cells mathematically Gi minus Ni. Gi cells are there. Out of that Gi cells, Ni cells are occupied by one particles. So, remaining cells will be there. that remaining cells are obtained by Gi minus Ni. These cells are empty. Now, the possible number of such a distribution is given by Gi factorial cells. That is, among the Gi cells, Ni cells are occupied with 1 particle each. So, the possible number of such a distribution is given by Gi factorial cells. Here, we have assumed the particles are indistinguishable. So, as the particles are indistinguishable and the occupied Ni cells are similar to each other, Ni factorial permutations of occupied cells will not give rise to indistinguishable arrangement, all will give rise to same arrangement. So, Ni cells are occupied, Gi minus Ni cells are remaining. Gi factorial is the mathematical expression for number of such distribution. Now, we know that the particles are indistinguishable and the occupied cells also similar, indistinguishable. So, that Ni factorial permutation of occupied cells will not give rise to indistinguishable arrangement. Further, that Gi minus Ni factorial, that is permutation of empty cells, gives rise to indistinguishable arrangement. So, we learnt that the occupied cells will not give indistinguishable arrangement, empty cells will give indistinguishable arrangement. That is the point you have to note at this juncture. Therefore, the number of distinguishable arrangement of Ni particles in Gi cell is given mathematically as Gi over Ni factorial into Gi minus Ni factorial. This is the mathematical expression for the number of distinguishable arrangements of Ni particles in Gi cells. Keep this as equation 1. For all quantum states, similar expression can be obtained. This is the expression for ith cell. If you want to know the mathematical expression for the first cell, replace all these things by 1. So, G1 by N1 factorial into G1 minus N1 factorial. This is the distinguishable arrangement of N1 particles in G1 cells. So, let us take the second quantum group N2. The second quantum groups N2s are arranged in G2 number of cells. So, you will get G2 by N2 factorial into G2 minus N2 factorial. Like that, you will get equations for all quantum states. Suppose there are N1 particles in first group of energy epsilon 1 and N2 particles in the second group epsilon 2, this expression will change as I said earlier, G1 by N1 factorial, G1 minus N1 factorial, G2 by N2 factorial into G2 minus N2 factorial. Like that, you will get different expression. Now, to get the total number of eigenstate for the whole system, you will get G is equal to summation over I Gi over Ni factorial into Gi minus Ni factorial. This is the expression for total number of eigenstates. In accordance with the so, we got an expression for the total number of eigenstates. Now, let us go to a priori probability of states. In accordance with the postulate of equal a priori probability of states, the probability omega of the system for occurring with the specified distribution is proportional to the number of eigenstates. So, we got an expression for the number of eigenstates. This expression can be used to get the most probable or probability for a particular kind of distribution. This is the expression for probability for a particular kind of expression. Omega is equal to summation over I Gi factorial over Ni factorial into Gi minus Ni factorial into constant. This is the mathematical expression for the probability of the system for occurring with the specified distribution. This is proportional to the total number of eigenstates. Keep these as equation 3. Now, come to the Fermi Dirac distribution law. So, to get the Fermi Dirac distribution law, we assumed 3 cases, then we got an expression for the number of ways if arrange a particle in Ni cells, then total number of eigenstates. Using the total number of eigenstates, the total probability of a system with a specified distribution is obtained. Now, Fermi Dirac distribution law is nothing but determining the most probable distribution in the case. This gives the probability of distribution for specified. Fermi Dirac distribution law is most probable distribution. To get that most probable distribution, take logarithm on both sides of this equation. So, the equation will change into log of omega is equal to log of pi I into Gi factorial over Ni factorial into Gi minus Ni factorial into constant, which is equal to summation over I log of Gi factorial minus log of Ni factorial minus log of Gi minus Ni factorial plus constant. Keep this as equation 4. In this equation, this Ni and Gi are large numbers. So, we have to use Stirling's approximation to reduce this equation in a simplified form. So, now using Stirling's approximation in this equation reduces to log omega is equal to summation over I of Gi minus log of Gi minus log Ni plus Ni minus Gi minus Ni into log of Gi minus Ni plus Gi minus Ni plus constant. In this equation, remember that Gi is not subject to variation and Ni varies continuously. So, just differentiate this, you will get the required probability distribution of Ni particles in Gi levels. Gi is a constant one, that is not subject to variation, and this Ni varies continuously. So, differentiation of this above equation gives del of log omega is equal to summation over I log of Gi minus Ni minus log of Ni into del Ni, which is equal to summation over I log of Ni by Gi minus Ni into del Ni. So, this is how this equation will change after applying differentiation on this equation. For most probable distribution, the desired probability omega should be equal to omega maximum. So, this del of log omega maximum must be equal to 0. Thus, the condition of most probable distribution gives summation over I log of Ni over Gi minus Ni into del Ni is equal to 0. So, to get the most probable distribution, you have to keep that omega as omega max. So, the differentiation will also be equal to 0. So, we got this equation, keep this equation as 7. Now, after obtaining that equation, we need to assume 2 subsidiary conditions. The 2 subsidiary conditions are the total number of particles of a system is constant, because in any system particle will not die out, either it will move out or come in. When the number of particles moves out, equal number of particles comes in. So, total number of particles is constant in a system. Therefore, n is equal to summation over I n I is equal to constant. Differentiation of constant is equal to 0 mathematically. So, the total number of variation of total number of constant is also equal to 0. So, summation over del n I is equal to 0. Keep this as equation 8. This is the first subsidiary condition. Now, the second one is total energy of the system is constant. So, energy conservation principle should also be obeyed by the assumed n indistinguishable thermal system, n particles of a thermal system. So, E is equal to summation over I n I epsilon I is equal to a constant. Now, del of E is equal to summation over I epsilon I del n I is equal to 0. Now, apply Lagrangian's method of undetermined multiplies, multiply equation 8 by alpha and equation 9 by beta and adding both. So, this equation should be multiplied by alpha and this equation should be multiplied by beta, and adding the resulting expression, so we get the equation in the form summation over I log of n I over g I minus n I plus alpha plus beta into summation over I del n I is equal to 0. So, as the variation del n I are independent of each other, we get log of n I over g I minus n I plus alpha plus beta epsilon I is equal to 0. Now, remove the logarithmic symbol here. So, to remove this logarithmic symbol, take this alpha plus beta epsilon I to the next side of this equation. So, you will get minus alpha minus of alpha plus beta epsilon I. So, we got n I by g I minus n I is equal to e power minus alpha plus beta epsilon I. This is how you will get after taking anti-log exponential of both sides of the equation. Further simplification of this equation gives g I minus n I by n I, that is both sides of the equations are inverted. So, the denominator comes to the numerator, numerator goes to the denominator, which is equal to this minus sign goes away. So, you got e power alpha plus beta epsilon I. So, g I by n I minus 1 is equal to e power alpha plus beta epsilon I. So, g I by n I is equal to, take this minus 1 to the other side of the equation, you will get e power alpha plus beta epsilon I plus 1. Now, get the value of n I from this expression. So, n I is equal to g I by e power alpha plus beta epsilon I plus 1, e power alpha plus beta epsilon I plus 1. Keep this as equation 11. This equation represents the most probable distribution of the particle among various energy levels for a system obeying Fermi Dirac statistics, and this is known as Fermi Dirac distribution law. So, Fermi Dirac distribution law gives the most probable distribution of the particle among various energy levels. This is how you can derive the Fermi Dirac distribution law using Fermi Dirac statistics. Next, we will see some of the thermodynamical, we will see the mathematical expression for some of the thermodynamical property of completely degenerate Fermi Dirac gas. You know, degeneracy means number of times a particle or a body or a system can be splitted, that is called degeneracy. If the system is cannot be splitted or separated means then the system is called non-degenerate. Here we are going to learn the thermodynamical property of completely degenerate Fermi Dirac gas. The first thermodynamical property is total energy of the system. The total energy is given as E is equal to 3 by 5 into n of total number of particles. N is the total number of particles, epsilon f of 0. This epsilon f of 0 is the Fermi energy, value of Fermi energy, into 1 plus 5 by 12 pi kT by epsilon f of 0 the whole square, pi kT by epsilon f of 0 the whole square. This is the total energy of ideal strongly degenerate Fermi Dirac gas. Then the next thing is pressure. First we have seen the expression for energy, the next thing is pressure. The pressure of ideal strongly degenerate Fermi gas is given by P is equal to 2 by 5 into n epsilon f of 0 over V into 1 plus 5 by 12 pi kT by epsilon f of 0 the whole square. This is the pressure of Fermi Dirac gas, a gas which obeys Fermi Dirac statistics. Next, specific heat capacity C suffix V, where the C suffix V is the specific heat capacity at constant volume, that is given by C suffix V is equal to dou E by dou T is equal to dou by dou T of 3 by 5 into n into epsilon f of 0 into 1 plus 5 by 12 into pi kT by epsilon f of 0 the whole square into V. This is the specific heat capacity of a Fermi Dirac gas. This can be further simplified as 3 by 5 into n epsilon f of 0 into 0 plus 5 by 6 pi k by epsilon f of 0 the whole square into 2t. This is the expression for specific heat of a Fermi Dirac gas. So, in this lecture we learnt the Fermi Dirac statistics. Under that Fermi Dirac statistics we derived an expression for Fermi Dirac distribution law. This Fermi Dirac distribution law gives the number of particles distributed in Gi energy levels. It gives an expression for the most probable distribution, Ni is equal to Gi by some factors. This Fermi Dirac statistics is obeyed by half integral spin particles. Some thermodynamical property of Fermi gas is discussed. We learnt that specific heat of ideal Fermi gas is proportional to the absolute temperature. These are all the concepts we learnt from this lecture. After listening to this lecture, you can answer the following questions. Give the assumption made in Fermi Dirac statistics, give the expression for entropy of a Fermi gas, state the Helmholtz free energy of Fermi gas. Thank you.